And we're going to look at implicit differentiation. So we've been doing derivatives, but all the functions we've been given have been in explicit form. So we've had the output on one side and then the input on the other. And so when we've been taking these derivatives, we haven't had to really account for, in a sense, for that output value. We have, but we've been doing it like intuitively. We've been saying that, hey, if y equals 2x plus 1, then y prime is 2, right? So this action here, going from y to y prime, we were doing the derivative with respect to x. We just didn't really, I guess, formally say that in a way, because the derivative of x is just 1, right? So the derivative of y is just 1, but we're doing the derivative with respect to x, so we need to say y prime, or another notation, dy dx. And we have been doing that, and it's worked out good so far. But when we're given functions implicitly, so the output is not isolated, we have to do things a little different in a way. So we can take equations as they are, and then we're going to find the derivative of both sides. And it's like we're doing a chain rule when we're doing anything that deals with y. So if I have y squared, it's like the outside function is that y squared. So the derivative would be 2y. But then I have to do the derivative of the inside, which is y, which is y prime, or dy dx. And so that's what we have to do every single time. So the best way is to just do a bunch of examples. So let's run through some. And then it might give us a point to use as well that we can plug in. Sometimes it will, sometimes it won't. So find dy dx for xy plus y equals 8 at the point 3, 2. So xy, that requires a product rule. So left, d right, the derivative of y, is going to be that dy dx, or that y prime. And then plus right, and then d left. And then the derivative of y is 1 dy dx. And the derivative of a constant is 0. And then what we do from here is, let me make that a dx better. What we do from here is we want to isolate the dy dx. Sometimes it's nice to have that function laid out explicitly for us. If we're going to plug in a point, sometimes I plug it in and solve later, but let's just solve for it first here, just because. So I want to isolate these terms. So I'm going to move y out of the way. So I have x dy dx plus dy dx equals negative y. Well, then I can factor out a dy dx, and I'm left with x plus 1. And then I can divide both sides by that x plus 1. So dy dx is negative y over x plus 1. And then when I substitute in that point, 3, 2, I get negative 2 over 3 plus 1. So negative 2/4, which is negative 1/2. Let's try another one. So x plus 3xy minus 2y squared equals 2 at the point 1, 1. So, all right, derivative of x is just 1. Another product rule here. I will section that as 3x and y. So left d right plus right d left. And then I have 2y squared, so I can do it normally. So 4y, but then I also have to multiply it by that dy dx. Let's isolate that dy dx again. So let's move everything else. So I have 3x dy dx minus 4y dy dx. I'll subtract 1 and subtract 3y. I'll factor out the dy dx. And then divide both sides by that 3x minus 4y. So dy dx is negative 1 minus 3y over 3x minus 4y. And now I'll substitute in that 1, 1. So I get negative 1 minus 3 and 3 minus 4 for a final answer of just 4. All right, we got some stuff going on here. We don't have a point to plug in, so we're just going to get the final function, isolating that dy dx and leaving it. So we have 3y squared dy dx plus 10y dy dx minus 5 dy dx minus 2x equals 0. All right, so let's, because I didn't make this box big enough for my handwriting here, I'm going to factor out the dy dx, and I'm left with 3y squared plus 10y minus 5, and I will have added the 2x over. Then I can divide by that big quantity. So dy dx is 2x over 3y squared plus 10y minus 5. All right, let's do another one. So find y prime for y e to the x equals 3 pi. So product rule here, left d right plus right d left. And then I will just subtract over. And my primes look like 1s. I should really like curve it. Now it looks like a 7. Oh my gosh. Maybe. I'll subtract over the y e to the x. And now divide both sides by e to the x. So actually, y prime is negative y. All right, got some trig functions here. Bunch of stuff going on. So derivative of the outside is negative sine of xy times the derivative of the inside, which is that product rule. So left d right plus right d left equals 1 plus 3 y prime. Then we want to isolate the y primes. So I'm going to do a couple of things. Let's see. I want to move the 3y prime over. And I think it might be easier if I just distribute the negative sine of xy into that quantity so that I can isolate some things. And now I'm going to make this xy prime in front. So negative xy prime sine of xy minus y sine of xy minus 3y prime equals 1. Then I'm going to move the term that does not have the y prime. So I got negative xy prime sine of xy minus 3y prime equals 1 plus y sine of xy. I'll factor out my y prime. So I get negative x sine of xy minus 3. And then I can divide by that quantity. So y prime is 1 plus y sine of xy over negative x sine of xy minus 3. All right. Got a chain rule here. This is natural log of u. So we do u prime over u, which needs a product rule. Left d right plus right d left all over u, which is just xy. And then the derivative of sine is cosine. And then let's isolate that y prime. So I'm going to multiply both sides by xy. And then I can subtract y. And then divide by x. So y prime is xy cosine of x. And I'm going to put parentheses around that because I have a minus y and I don't want the I don't want it to look like it's cosine of x minus y. And all over x. And there we go. Let's go a little further. So given an equation, let's find the equation of the tangent line at x equals -1 and the normal line. So I need a point and a slope. So let's find the point. So I'll substitute in -1. So -1 squared minus -1 times y plus y squared equals 7. So I get 1 plus y squared equals 7. Then I have like a quadratic in the y form. So let's subtract 7. Make this a little prettier. So y squared plus y minus 6. And then I think I can factor that y minus 2, y plus 3. So I get y is 2 and y is -3. So I have 2 points. So I'm going to have 2 equations. So I got -1, 2, and I got -1, -3. So let's do the derivative to find the slope. So 2x minus, because I'm going to be subtracting over that quantity, I'm putting in a big bracket. So left d right plus right d left. And then, all right. I'm going to clean it up by doing this. I have 2x minus xy prime minus y plus 2y y prime. And then I'm going to do 2 different things. I'll do it with this one. And then I'll do it with this one. So I'm just going to substitute in. So I have 2 times x minus x y prime minus y plus 2y y prime equals 0. So I have -2 plus y prime minus 2 plus 4y prime. And I get 5y prime equals, I'll just add both of those over, 4. So y prime is 4/5. So the equation for this one is y equals 4/5 x plus 1 plus 2. Then I'll do the same thing for the blue one. So we have 2 times -1 minus -1 y prime plus 2y, y prime is 0. So -2 plus y prime minus 6y prime. Oh, I think I have made a mistake here. Nope, I forgot to do it in this one. I'm going to rewrite this one. So 2x minus xy prime minus y plus 2y, y prime is 0. So -2 plus y prime plus 3 minus 6y prime is 0. So I get -5y prime this time. And then that would be 1, so I'll subtract it over. So y prime here is 1/5. So that equation is going to be y equals 1/5 x plus 1 minus 3. And then remember, for the normal line, we have, here I'll do the 2 different colors. I got my blue one and then my yellow one. The only thing we switch are the slopes. So if originally the slope was 4/5, the normal line is going to be -5/4. And that's the only thing we change. So y equals -5/4 x plus 1 plus 2. And for the blue one, the slope was 1/5. So the normal line is -5. So y equals -5 x plus 1 minus 3. All right, this next one, we have 2 derivatives. So let's find the first one. So cosine of y, it's going to be negative sine of y times y prime equals 1. Isolate y prime, so y prime is 1 divided by, I'm going to put the negative up top, so -1 over sine of y. Now I need to do a second derivative. So low d high minus high d low all over low low. So I'm going to clean things up. Shouldn't have wrote so big and such in the middle, but sine of y times 0 is just 0. And then negative and a negative is going to make a positive. So that's cosine of y, y prime over sine of y squared. But I don't want a y prime in the answer, but I solved for y prime, right? So I need to do that substitution. So that's cosine of y times -1 over sine of y over sine of y squared. And really, I can drop that sine of y into the denominator here. Or, yeah, here's what I'm going to do. I'm just going to make that a negative cosine of y. And then I'll do my big C over little c trick here, right? Big C over little c. To get negative cosine of y over, it's actually going to become sine of y cubed. Ta-da. All right, find the points at which the graph of x squared plus xy plus y squared equals 27 has either a horizontal or vertical tangent line. So what that means, a horizontal is going to have a slope of 0. So that's going to be y prime set equal to 0. A vertical tangent line, right, is a slope that's undefined. So if we have a fraction here, we would set the denominator equal to 0. But I don't think we have that here. So let's do a derivative. So 2x, and that's a product rule. Left d right plus right d left. And then 2y y prime equals 0. All right, let's clean it up. Let's move everything that doesn't have a y prime to the other side. So minus 2x minus y. Let's factor out a y prime. So I'm left with x plus 2y. And then let's divide both sides by that x plus 2y. So y prime is negative 2x minus y over x plus 2y. So, okay, I do have a fraction here. So, I need to find when this whole thing is equal to 0. Let's do that first. Negative 2x minus y. Well, okay. Well, no, I'll do the whole thing. So negative 2x minus y over x plus 2y equals 0. Okay, I'd multiply both sides by x plus 2y. But 0 times that is just going to be 0. So I just need that numerator set equal to 0. Then I have two variables here. Find the points at which the graph has either a horizontal or vertical tangent line. I definitely didn't leave enough space here. So I could add y to both sides, and I will have horizontal tangent lines when y equals negative 2x. So if I go back to the original, let's solve that. So x squared plus x times y, and then plus y squared. And I can solve for my x values from here. So that's x squared minus 2x squared plus 4x squared equals 27. So let's see, 1 minus 2 is negative 1 plus 4, that's 3x squared equals 27. So x squared equals 9. And, oh, I'm out of room here. X equals plus and minus 3. Okay. So let's figure out what those points are. So I have 3 and I have negative 3. So I can plug that in to this y value here, right? So 3, that's going to make negative 6. Negative 3 is going to make positive 6. So that's where we have horizontal. So 3, negative 6, negative 3, positive 6. Now undefined is the denominator set equal to 0. So x plus 2y set equal to 0. So let's solve for y again. So 2y is negative x, and then divide both sides by 2. So y is negative 1/2 x. Let's do the same thing and substitute. So x squared plus x times negative x over 2 plus negative x over 2 squared is 27. So let's see here. We got x squared minus x squared over 2 plus x squared over 4 equals 27. I'm out of space here, but let's see what happens here. We got 1 minus 1/2, so that's a half. So 2/4. 2/4 plus 1/4 is 3/4. So 3/4 x squared is 27. Then I would have to multiply by 4/3. 9 times 4 is 36, so we'd have x squared is 36, which means x is going to be plus and minus 6. So 6 and negative 6. And I can plug that back in to my y equals here. So 6, half of that would be negative 3. If I plug in negative 6, half of that is positive 3. And there are the points that give horizontal and vertical tangent lines. And that is all for implicit differentiation. So if you have any questions, let me know.